Okay, let's have a look at the OPAL paper. And here it is. And this is about assessing taxonomic metagenome profilers. And metagenome profiler is a tool that do taxonomic classification and then predict the abundances of all the taxa in there, right? So that's what we are looking at, assessing this. And let's scroll down to this section here called metrics and accompanying visualizations. So the very first thing we look at is this preliminaries. For R, a particular taxonomic rank. Consider a rank in a taxonomy, and we now stick to the species rank, but this could be easily done for all ranks, right? So if you classify it to the species, you consider the species rank, but if you classify it to genus, you consider the genus rank, and so on, right? So R is used to sort of indicate any rank then, but think of it as species now. Let XR be the true bacterial relative abundances at this rank given by the gold standard. So we need a gold standard, of course, right? It's impossible to know how well these profilers or these taxonomic classifications are unless you have some truth to compare it to, right? We need a gold standard. So here I have a gold standard. And this is a very small metagenome because it has only 3 different taxa, 3 different species. And I denote them by tax ID here instead of name. I think that's better because names are shaky, right? Tax IDs are the more accurate way of organizing them, displaying them or naming them. So we have relative abundances here, the true abundances. This is what we would try to predict, right? These 3 only, and 50% of this one, 30% of this one, 20% of this one. Here I have written it in a vector like they say here in the paper, right? XR is now this vector here. And the numbers here are simply row numbers or indexes, right? So it's taxon number 1, 2, and 3, value number 1, 2, and 3. 1, 2, and 3 here. Okay. And then we need, of course, a prediction. So XR star is a vector of predicted bacterial relative abundances for the same rank, of course. So let's add some predictions. And here they are. We add them as a new column to the same table. And then we see a couple of things immediately here. First of all, we notice that in these predictions, there were 3 new taxa here that were not originally in the gold standard. So the table grows. And how do we make this table? Well, we had the gold standard table, and then typically we have a new table with the predictions on also tax IDs, and then we join these 2 tables by the tax ID. So we make sure that the rows that correspond to the same tax ID are matched against each other, right? And that's why I called it a joint table. This full is the joint table. We will do this in the exercises. We also notice these are not relative values like it is here. These are probably read counts or something. We should turn this into relative values. We will see. And also, we see there are some holes, of course, in the table, because these 3 taxa were not in the gold standard, so there are some empty cells here. And also this taxon, 1002, were never predicted, so it's an empty cell here as well. So what we have to do now is to make sure that we have these relative values in the gold standard and also relative values in the predicted abundances. And also we have to fill in this empty cell. So the very next thing we do now is to compute the relative values here. And how do we do that? Well, if you go back to the previous, if you sum all the values in this column, you get a total sum. And then you take all the elements and divide by that total sum, of course. So then you have the relative values. And as if you If you notice, the sum here is 1000, and that's why the numbers here are pretty. And then we fill in with zeros in all the empty cells, because abundance being absent means that the abundance is actually 0. So in this case, missing value is the same as 0, because it's sort of a count, right? You count reads or whatever, and if it's not counted, it means count 0. And here we now have the corresponding vectors xr and xr star. These are just columns, right, of this table. Okay, let's go back to the paper here. The next, or the very first thing we want to do is to assess the profiler based on presence or absence of the taxa. And in order to do that, we need to decide what is present and what is absent. And that's what this formula here, or this metric here, is all about, the support. The support of a vector, in this case the gold standard abundance vector, the column, the support of it, what is it? And let me read out loud. The set of indexes I such that the abundance number I is larger than 0. That's what this expression says. And notice the threshold 0 here, right? The indexes I such that the abundance is larger than 0. If we go back to our small example, what does the support for this vector look like and the support for this vector look like? Here they are. The support for this xr vector is the set 1, 2, and 3. So these are the indexes, the row numbers, where the corresponding abundances in this column is larger than 0. Right? This is larger than 0, this is larger, this is larger, but this is not larger than 0 because it is 0. Right? So that's why the support of this one is 1, 2, 3, because it's the first 3 elements that are larger than 0. And we see the support for the predicted vector over here is this 1, 3, 4, 5, 6, not 2, because 2 is 0 here, right? So this is the support of these 2 vectors. And then from these supports we can compute our old familiar stuff: true positives, false positives, and false negatives, like this. And notice the true positive, that's the intersection between the 2 supports and the size of that intersection. Right? So what we actually do, let me jump one. We take the support from this one, 1, 2, 3, and the support for this one, 1, 3, 4, 5, 6. What is the intersection between them? Which elements in this is also an element in this? It's 1 and 3. And the size of that is 2, because there are 2 elements, right? So here we have the true positive, 2. 2 true positives, and we can see it directly from here, right? Because this is predicted and it's also true. This is predicted positive, and it's also true. So there are 2 true positives. The false positives, that's the intersection between the complement of this support, right? This is what this means. The complement of the support. And what is the complement? Well, if you have the support up here, the complement is all the indexes that is not part of this support. That's the complement, right? All the indexes, say 1, 2, 3, 4, 5, 6, 3 of them are in the support, and then the 3 others are in the complement of the support. And the same down here, right? Here is the support, and the complement is then the element which is not in the support. So if you take the intersection between the complement of the gold standard support and the support of the prediction, that means the intersection between this set and this set, and you can see 4, 5, and 6 are in both. So the size of that intersection is 3. And the same for the false negative here, and you get size 1 because there's one element here which is also part of this here. Yes, so true positives, false negative. I mean, this way of writing it is a little bit, I feel, unnecessary mathematical, because it's so much simpler to see it from the table, isn't it? True positives, those who are present in both, right? False positives are those who are present in the prediction but absent over here. That's these three. Right? And the false negatives are the reverse. They are present in the gold standard but absent in the. So that's so much simpler. Okay. Once we have these three here, we can compute the good old precision and recall. And of course, these people here, they have invented some new name for precision and recall. They call purity, which is the same as precision. Or specificity, they say, and this is dead wrong. This is not correct. Precision is not the same as specificity. You can look up specificity, it's not the same. But and they use it. I don't know why they have to invent a new name for it. It's a rather stupid thing to do, I would say. Why don't you use precision that we know everyone knows what it is? And here it's a formula, and we recognize the formula, right? You should have seen this before. They also call completeness. That's recall, right? Or sensitivity, and that's correct. Recall or sensitivity, they are synonyms, meaning the same thing. And here you have a third synonym now. If you want to make yourself important in this world, invent new words for old ideas. And here we recognize the formula. So if we go back here and compute based on these numbers here now, we can compute precision and recall. Then this is the precision. Quite bad here. Recall, also not very good. We would like both of them to be close to 0, right? They also introduced the Jacquard index here. First of all, this F1 score, I don't mention it. You can see it's just a product. It's a way of combining precision and recall into one single number. Have a look at it if you like. But more interesting, or I would like to mention this Jacquard index, because we have talked about Jacquard indexes before when we talked about the mesh distances. So here is how you can compute the Jacquard index, and here they use this very mathematical formula, I would say, unnecessary again, because what you see in the numerator here is actually the true positives, and what you see in the denominator here is actually true positives plus false positives plus false negatives. If you add them all three, then you get this one here. And actually, it's I would say it's easier to look at it over here, because Jacquard index is simply the size of the intersection between these two columns. The present stuff, right? That's this one, and divided by the size of the union. So the size of the union is actually the number of rows you have, right? The union, that's the total number of taxa in the whole data set here. And then the size of the intersection is the 2, because it's these 2 rows here, right? So it's 2 divided by 6 then. Notice that the reason why, and this is also quite poor, right? We would like this to be close to 1 as well. Then the prediction is very close to the gold standard. And the reason the prediction is now very different from the gold standard is partly due to these 2 here, very much due to these 2 here. And this questions again this threshold of 0. If we scroll back a little bit here to that support, right? This here. We say that it has to be larger than 0 to be present. Anything above 0 is present. Is that really the case? I mean, these are very small values. I would say that when you have this low abundances, these taxa are hardly present in my data. This could easily be due to some noise here, right? The reads have been misclassified into these two taxa. A few reads, right? Few reads only. So when the abundances are this low, I could easily call this absent. So actually using a threshold at 0 is a little bit sort of extreme. I would at least allow this to be a little bit above 0, so that these two are actually also are not part of the support here, right? If you take 5 and 6 out of the support here and then compute over again, you will see that the results are not that bad after all. But they become bad because of these two here. Okay. Let's look at abundances instead, because then we don't need to don't need these thresholds, and that's an advantage of abundance. When we compare the abundance, how do we compare the abundances? Well, they suggest we use the L1 norm, and here is the formula for it. And what is it? Well, sum over all the indexes the following. Take the abundance from the gold standard, number I, subtract the corresponding abundance number I from the prediction, and take the absolute value of this, and then do this, sum this over all indexes. That's the L1 norm, which is also the same as Manhattan distance. We talked about Manhattan distance in another context, and it was about this pan matrix trees. It was actually the same formula. I didn't present the formula then because then all the values were either 0 or 1. Here we have abundances, which are decimal values, right? But if the values are 0 and 1, you can express this in a different way, but this is the general formula for L1 norm or Manhattan distance. And here's how we actually compute it now. So here I've written the formula again in a slightly different way. First of all, I specify that I goes from 1 to 6, since we now have 6 indexes, right? So we sum over all indexes, and what do we do inside here? We take abundance number I, and I use the brackets like we do in R. Abundance number I from this column minus abundance number I from this column, subtract them and take the absolute value. And that's exactly what we do over here. So notice we start with I equal to 1. First row, we look at the differences. 0.50 minus 0.60, and then take the absolute value, so you get 0.1. And then plus, we go to the second row, minus 30 minus 0, 0.30 minus 0, an absolute value becomes 0.30 here, which we add to the first one, and then we proceed down the table like this, right? Looping, you could say. But you don't really need to do the looping in R, but that's another story. But in principle, it's a looping, right? You compare element by element by element here. And of course, if the abundances here were exactly the same as the abundances here, then all the differences will be 0 and the total sum will be 0. So if you have a perfect prediction over here, then the L1 norm becomes 0. That's the best you can have, right? The Manhattan distance of 0 means there is no distance, right? There is no difference between them. They are identical. But on the other hand, what is the worst possible distance you can have? How big can it be? Let's imagine that the prediction had zeros in the first 3 rows and then some positive values in the last 3 rows. So that you compare a value here to 0, compare to 0, compare to 0, and then compare 0 to this, compare 0. Then you have the maximum distance, which is the sum of the values in both columns. And we know that the sum of the values in each column is 1, so the sum of both is 2. And that's actually the largest distance you can have here, 2. as long as you have these relative abundances. Then the paper introduces the Bray-Curtis distance, and this is really surprising to me. And here's the formula for it. And have a look at this formula. See that the numerator here is exactly the same as the L1 norm up here. Can you see that? 100% identical. And what is in the denominator here? It's the sum of all the gold standard abundances. But that's 1, right? The sum in this column is 1. And then the sum of all the predicted abundances. Yeah, but this is also summed to 1, right? This was required. This was required a few lines above here, that we should do this. So what you actually do here is you take the L1 norm and you divide by 2. 1 plus 1. So what's the point of that? What's the point? I mean, if you have computed the L1 norm, then you compute it again and divide it by 2. I mean, that's the same thing, right? Whether you compute it here or compute it again and divide by 2, what's the point of that? So instead of having a value that goes between 0 and 2, you have a value that goes between 0 and 1. But these two will measure exactly the same thing, right? So it's pointless to have them both. You can choose one of these two, but not include them both. I don't understand why they have this both in here, as long as they do this. I would not have done that. Choose one of them. And then finally, I will just say a few words about weighted unifrac distance. There is no formula for it here, and that's a good reason for why it's not a formula, because it's too complicated. But I can I can try to illustrate the idea behind a weighted unifrac distance. So with the L1 norm now, or Manhattan distance, or the Bray-Curtis for that matter, we now just compare the values between the predicted and the true abundances, right? And it came out, well, not super bad, but not super good either here. And why did it come out with this large L1 norm? Well, very much has to do with this row here, row 4, and row 2, right? Because here in row 2 we have taxon 1002 is actually quite abundant, but we predict it not to be there at all. It's a big miss here, right? And here in row 4 we have a big miss the other way. This taxon here should be not in here at all, abundant 0, but we predict it to be quite abundant. So you can see this one, this miss plus this miss is 0.49, right? Almost, yeah, majority of this due to these two misses. But what now if this taxon here is a very close relative to this taxon here? It's not the same since there are two different tax ideas, but this could easily be a species which is very closely related to this species here. So that actually we claim that these reeds are from this species, but we are now confusing it with this species here, and we should actually have assigned these up here. So if that is the case, then the picture is not as poor as it looks like now. Do you agree? You missed, but you missed only with the neighboring species, you could say. And that is exactly what the weighted unifrac distance is trying to include into the distance measure, right? That we have to actually look at the tax ideas here and see which of these taxa are closely related and which are more distant related. And then we should take that into consideration in a way that makes these differences a little bit more reasonable. So a weighted unifrac distance is more cumbersome to compute because then you also need sort of a phylogenetic tree for these taxa, saying something about which is closely related and which is more distant related. And then you have to use this as a weight when you compute these differences here. It's actually sort of an extended Manhattan distance in a way, but with some weights. So for instance, this difference here and this difference here will be weighted down and not count as much anymore if this taxon and this taxon is very closely related. But if they are not, if they are very distant related, then they are perhaps weighted up, so it becomes even worse than it looks like now. But that's the idea of the weighted unifrac anyway. And then I think we are happy. This alpha diversity metrics we don't talk very much about because they are not really very useful for what we are doing here. And beta diversity metrics, that's exactly what we have been looking at now. Both the L1 norm, the Bray-Curtis, and the weighted unifrac are examples of these beta diversity matrices. And when it comes to visualizations, we will actually look at that in an exercise where we plot what we call a stacked bar chart. So I will not use the paper for that. So I think that's what we need.